is Electronic and Space Systems, Ryan Aeronautical Company, San Diego, California. Being manufactured here is the landing radar system for the Apollo Lunar Module, the spacecraft that will place America's astronauts on the moon. Tiny electronic parts assembled in a clean room atmosphere. Transistors, resistors, capacitors. Integrated circuit chips bonded with gold wire. Assembled in cordwoods, each circuit is protected from the harsh environment of space by a vacuum-forced coating of polyurethane. Inspection procedures are exacting. Hardware for manned spaceflight requires perfection in workmanship. Each subassembly is tested. Each frequency tracker, each signal processing board is made to do its stuff on the test bench. The finished electronic assembly contains trackers, processors, and the power supply. Many things are unique. One is the elimination of interconnect cables by the use of an interconnect board on which the wires are etched. A special wire wrap tool finishes the job. The black box is ready. For the radar antenna assembly, skills of the master machinist are needed. With great precision, the microwave plumbing is cut and drilled from magnesium. Other parts are handled in batches on numerically controlled drilling machines. The finished part will guide the path of the microwave radar energy. Antenna faces are machined from magnesium plate and assembled with the care of a silversmith. The design is called a slotted planar array. Antenna accuracy is refined for each of the 15 radars slated for space missions. Mounted on a granite slab in a 40-foot high tower, each antenna is bore-sighted, tuned to an accuracy of plus or minus 4 minutes of arc. Radar energy is transmitted to a second tower 280 feet away, received by a pair of accurately positioned horns, and reflected back to the radar receivers. Qualification testing of prototypes. Pre-delivery testing of spaceflight hardware. The system is tested and checked. Vibration and shock, temperature and humidity. All this in preparation of the astronauts' electronic eyes. Most rigorous among qualification tests was acceleration. The antenna assembly mounted inside the white container was spun to a force of nearly 7½ times normal gravity. Another test placed a Ryan landing radar in a radome mounted beneath a NASA helicopter. The year-long flight test simulated the radar-controlled descent to the moon. Space hardware receives the final touch, a thermal coat. Chips of aluminum vaporize in the vacuum chamber, depositing a thin reflective layer on the spinning antenna. Next, most of the surface is masked to remain reflective while portions over the waveguides are sprayed with special white paint. Thus, the proper balance between reflecting and absorbing heat is achieved. The tape is removed, and gradually the finished radar antenna is revealed. The atmosphere is near that of the hospital surgery room. And that's it. A precision job, a refined technique, a blending of skills in electronics and metals. Next, the landing radar is accepted by RCA, which is responsible for radar subsystems on the lunar module, and then delivered by Ryan to Grumman, prime contractor, where it is installed on the lunar module. That's the how of it. Now for the why. Helping the Apollo lunar module land softly on the moon is a Ryan landing radar system. The radar antenna is positioned on the bottom of the descent stage of the lunar module, and the radar's electronics that process the radar's measurements are inside the descent stage. These measurements are of the speed of the spacecraft, how fast it's going forward and how fast it's going down, and of the spacecraft's altitude, how high it is above the moon. Radar energy is transmitted and received in narrow beams. The radar echoes come back from the surface of the moon. A shift in the radar frequency, called a Doppler shift, is measured to tell the velocity. Made of magnesium, the antenna is protected from extremes of temperature by a reflective coat of aluminum. Radar information is displayed on the astronaut's control panel and is fed to the guidance and navigation computers. Now, this is how the Ryan radar works in the moon landing. 7 minutes, the final crucial minutes in the Apollo program to land American astronauts safely on the moon. And aiding the lunar module in its descent is a landing radar system designed and built by Ryan Aeronautical Company of San Diego, California. Powered descent begins at about 50,000 feet. In the next few minutes, the descent engine will slow the spacecraft from its present speed of more than 3,700 miles per hour to a safe, radar-controlled 3 miles per hour at touchdown. Shortly after ignition, the landing radar is turned on and given a 30-second warm-up. Then, at about 45,000 feet, the astronauts initiate a yaw maneuver, turning the lunar module over with the viewing ports face up. In this position, the landing radar beams are directed at the lunar surface, and the radar altimeter locks on. Forward speed, about 2,700 miles per hour. Speed of descent, about 37 miles per hour. 7 minutes to touchdown. Some 90 seconds later, the lunar module has dropped to about 39,500 feet. At this point, the radar altimeter, having direct lunar contact, begins to update the inertial guidance system, which until now has served as the astronaut's principal sensor. The craft is now at 24,000 feet, 950 miles per hour, 4.5 minutes from landing. At about 59 degrees off vertical, the most forward-looking of the 3 velocity sensor beams strikes the lunar surface and locks on. Now the landing radar is serving as the astronaut's primary sensor in controlling the spacecraft's rate of descent. It has become their electronic eyes. Now, automatically, it updates the inertial equipment, displays altitude, rate, and velocity, and also automatically stabilizes the spacecraft during its descent. Radar reliability is a must. Near 7,000 feet, the lunar module reaches Highgate, a critical point in the trajectory. Velocity is reduced enough to bring the craft still closer to the lunar vertical. Shortly after Highgate, the landing radar switches automatically from the descent position to the hover position. And now the astronauts have their first low-altitude look at their landing site. They have now pitched forward to about 47 degrees and are at an altitude of about 6,800 feet. 5,000 feet, 2.5 minutes. 3,200 feet, 2 minutes. Forward speed slows to about 125 miles per hour as they pass the 2,000-foot mark. Descent rate is about 37 miles per hour. 1,000 feet, 80 seconds. 500 feet of altitude, low gate. The astronauts are crossing the lunar surface now at 45 miles per hour. Descent rate slows to about 15 feet per second. 60 seconds from touchdown. At 25 seconds, they pass the 200-foot mark. Gradually, spacecraft speed is reduced until at about 110 feet, descent rate drops to 3 feet per second. During this period, the astronauts take manual control of the lunar module. Using precise low-altitude measurements of their landing radar to maintain their desired descent rate, the 2-man lunar module continues to settle toward the moon. The astronauts assess their landing site and, if necessary, maneuver laterally by firing the reaction control jets. The best possible site is selected. The astronauts, cushioned by rocket power, guided by radar eyes, slowly, slowly, and touchdown. The soft landing, high point in man's greatest adventure.